Hello there. So in this video, I'm hoping to make it pretty streamlined, and I'm starting here with a VELMA GUI that has a VELMA XML loaded into it, of course, and then this PowerShell window here. Don't have to use PowerShell, just say that up front. You could use command line. I like using PowerShell though because it supports drag and dropping of file paths. So, you know, your VELMA jar, your XML, you can just get it from a folder and drag it straight into the PowerShell window, and it will then transfer the full file path for you. So it's pretty nice. As you can see, some of my file path names are quite long, so which is typical of me at least. But how do you get from this VELMA XML setup to this PowerShell window? And I'm hoping to make that seamless, but it's a bit of a roundabout, I guess, a way of setting this up. And the reason is because you would be doing this so that under multi-mode, you could have a separate simulation flowing into a current simulation. And so that's the point of this video here, is showing how to set up VELMA multi-mode in a way that a prior simulation run results are being fed into a downstream section of the watershed. And I have many windows open here, so let's see, that's not it, that's not it. This is the report. What do I want? Sorry about that. Thought I had everything prepped, but I'm not seeing. Oh, I think I saw it. Here we go. So in this example here, this is a write-up I'm working on to follow this. Not quite done, but I did include, well, let's start up here actually. So when you're setting this up, you need to have an upstream VELMA simulation, and you're going to run that first. And then you're going to set up a downstream section with including a dim roll-off, which we'll talk about. And that is specific to this setup. So in this video here, I'm focusing on the idea that you have an upstream simulation flowing into a completely separate, focused-in downstream simulation, which the example is going to be this Carnation floodplain area. Here we have the Tolt River, which is the upstream simulation that is going to be ran first, and the inputs are going to be off over to the east, and then those are going to then float into a high-res focused-in area. And so we had a 90-meter, we have a couple setups. We have a 30-meter Tolt run flowing in, and we have a 90-meter and separate 90-meter Snoqualmie setup flowing into here. So it depends on, are we focused in on only this area above the Snoqualmie, or are we worried about the Snoqualmie flow coming in to this floodplain as well? But for here, to keep it a little simpler, I'm just going to focus in on our setup that has just the Tolt flowing in, and we were focusing on this southern riparian zone restoration area. So the Snoqualmie, when it floods, backs up into this floodplain area, maybe this one a little bit, but regarding our flow paths, it doesn't influence this section along the south side of the Tolt. So, but yeah, so how would you set that up? How would you have, you know, or why would you set it? Actually, let's back up why. So we're running the Tolt floodplain at 3-meter resolution, and it's on the order of, I don't know if this might even say, yeah, so 3-meter resolution, 843 by 677. That's our column row count. So a lot of pixels. And you know, you multiply those two together, and you know the size of your overall map. But you know, at 3-meter resolution, this is a moderate sized VELMA run. But if you were to expand out your area of interest at 3-meter resolution to include all of the Tolt and all of the Snoqualmie River, then it would be massive. And it is massive. I can actually show you that. So here, this is that 600 something by, I don't remember now what the numbers were, but this is the 3 meter tolt setup versus this is part of the Snohomish setup, but this is that Snoqualmie River, these 3 subbasins, and then all of these here, this is all of our tolt subbasins. And so for people who are familiar with this at all, there's the tolt, here's another section of the tolt, and then this is the North Fork of the tolt, this section right in here. And so, but all of this area then contributes flow into this floodplain, including under some scenarios even this larger Snoqualmie. So imagine this little tiny box here is already approaching like 1,000 by 1,000 cells. Again, we could look at what it was. It was what, 843 by 677. So already pretty big, and yet it would just be monstrous at this level. It's just be really too large. You need a ton of RAM, and you would probably set this up in VELMA Parallel, which that's not unusual. We do that just to speed up processing, take advantage of parallel mode. But it'd really be a memory allocation, model initialization, just a massive problem for this huge area. So alternatively, what you can do is you can run this huge large area, because you need to. You need the contributing flow into the floodplain area. Well, actually, I should focus in on this section since this would be tolt only. But you could focus in on this tolt area here, and then run these results for, say, 10 years. You know, daily results from VELMA, and then feed those results into this 3 meter section only at the same timeline, 10 years. But basically, you're running this very large area that isn't the focus. But you need those flow results, so you run that and you get those results at a lower resolution, and then they get fed in along a flow path into these high-res results, where you want to see a lot of little, you know, the detail of the simulation. And so in this example, what we're looking at is flow and stream temperature impacts based off the restoration work in this section here. And so we need high resolution detail because we're modeling almost to the level of individual trees getting planted in this south zone here. And we broke up the south zone overall into 4 pieces in VELMA. But then, we need the flow results coming from the tolt, because this orange area here, this is the tolt river, and these are some side bank contributions into the tolt river. And ultimately, the south subfloodplain flows and joins in with the tolt right before the junction into the Snoqualmie. And so we want to see the impact of various ecosystem services occurring in this zone here at high detail, 3 meter detail. But again, stressing the point that we need the contribution from the Tolt River itself, which is a fairly large system to run even by itself. So how do you do that? Focusing in on here, you'll see that this is my delineated area all the way up to here. But again, my focus is actually right in on this area. But we use the same setup for if we're running the Snoqualmie with this floodplain area, or if we're running just the Tolt with this focused in little area. The input results being fed in might be a little bit different, but this is our 3 meter focused in area overall. And so focusing on the Tolt part of this, here is the flow path. That's key here. You want to be focusing on the flow paths. So what I have here is I have the delineated area for my watershed, and then from JPDM I also have the flow accumulation, and then with a little manipulation in the symbology, I'm then overlaying the major flow paths with my DIM. And so this would be for the high-res simulation. And then you then also need to step over into your low-res upstream contributions that you're going to run first. And so that is these. And so what you want to do is inside the boundary of your downstream simulation here, well inside the boundary, you want to correlate where there is a flow path along your high resolution along with a flow path with your low resolution. And getting away from the edge is important, and I'll talk about the edge here in a minute because it's a little bit unique. But moving along here, there's a lot of opportunities. This this might be a good one right here, where the flow path is right up through the middle of these pixels here. Because the resolutions are different and these are coming from completely different DEMs, the flow paths aren't going to be perfect. This is a really coarse. This is 90 meter pixels here, and so it's quite coarse. But overall, they end up following along the same general flow path overall. If I zoom out a little bit, it comes in and works its way out. And so, it's not perfect. We didn't dredge this, so we could have enforced this flow a little bit better. But the point here regarding the multi-resolution is that you have this flow path coming in generally in the right area, and then what you need to do is pick a XY cell position in both of these setups. And so, maybe I pick this pixel as my delineation pour point in my low-res setup, and then inside here, I then pick one of these pixels. I'd probably pick along the major flow path. So, I wouldn't pick something that's part of this little extra little piece here, but I'd probably pick one of these pixels here that's along the major flow path that would then continue on. So then when you run the simulations, the low-res simulations ran first. All the data, daily data, has all been generated to this point, this far down in the system, which is results for, again, all of this at low-res. And then in phase 2, you then run a second VELMA simulation that is then accepting those flow results from the low-res simulation that's already complete, and then feeding them in to the high-res simulation at the place that you select. And so that's why you want them to spatially line up and match with one another.